letter2Vec, and we got to figure out how are we going to get vectors out of letters. And we saw last time what you can do is you can train a neural network to do a prediction task, right? And when it was word2vec, we were predicting the next word. We had these like sentences, and then we were like removing. Some we were like, can you predict the next word? So for letter2vec, it's going to be the same kind of thing, except we're going to predict the next letter. And the thing we got to do is we got to figure out how are we going to fit these into our system. So can we draw a little diagram like we did last class with encoders and decoders? Can we draw it and make it make sense for letters? And last time we were doing the MNIST data set. So on the MNIST data set, what was the inputs and the outputs were the pixels, x1 to x728. So the first pixel, the second pixel, and so on. But of course, there are no pixels anymore, and they were doing letters. So let's make a new page here and say we're doing letter2Vec. Letter2Vec. So we want to input, somehow we want to input letters, a letter. For example, maybe you input the letter E, okay? And then that's going to go in, and then the output is going to predict the next letter. Output. Predict the next letter. Okay. That's roughly the setup. And we're going to talk about how we make the data set and so on. But actually, a better example, instead of inputting the letter E, let's input the letter Q. So if you input the letter Q and you want to predict the next letter, what would be a good prediction? If I'm writing down, you're watching me write things down. I'm going I'm writing English, and then I write the letter Q. U, yes, U, exactly. U is likely to be, so the predicted next letter is likely to be U. So that's what we want the network to do, right? It's going to input letters and output letters. I'm going to tell you more in detail about how we make the data set. But very roughly speaking, the data set is like all possible letter combinations. And we want it, so when you input Q, it's very likely that it outputs U. Okay, but of course, there's no letters anywhere in anything we've done before, right? It's all vectors. So we got to find a way to think of the input of a letter Q as a vector. We got to think of the output predictions, that's going to be some kind of vector. And we got to think about how are we going to make these things work using the things we already have. So that's what the question is. Is there any questions about the question? So let's see exactly what it says. In Mathematize, it says, the input is a vector of size blank. Okay, so we know the actual input is a letter, like the letter Q. But we're going to represent the letter Q as some vector, right? And we're going to input it into here. And there's even more. It says using blank encoding. So we're going to somehow encode the letter Q using blank encoding and get a vector of size blank. And then we're going to run it through our neural network. So we're going to encode it into some input vector. Then it's going to go into the machine, the neural network machine, and it's going to come out. And when it comes out, it will be a vector of size blank. Okay, so this is the input vector, and this is the output vector. And once again, when you have an output vector, that's not actually what we want. What we want is an output probability. So that's the second part of the Mathematize question. It says, the output is a vector of size blank, and we can interpret the outputs as probabilities by using blank. So first of all, how big should this be? And how are we going to do this step, this last little step of taking the output vector and interpreting it as a probability that says, oh, 99% chance it's a U coming after Q. That's the question. Is there any questions about the question? Makes more sense now? Okay, so take a guess. I think it's okay. If you guys take a guess here, it's okay to be wrong. It will help me understand how this neural network stuff is going for you. So let me give you one more minute on the timer to do this. I don't want this one. Okay. Okay. Yeah, I'll give a minute 40 because it's already up. Why not? And feel free to discuss with your neighbors what could the size of the vectors be. Who needs more time? Who's still thinking? Okay, put in a couple people. Put in your final guesses, and then maybe we'll do another round if people are still stuck. So I'll give you a couple seconds here to put in your final guesses. Just put in a guess. It's okay to be wrong, as always. Okay. 1, 2, 3, 4. Okay. That's roughly about the number of people in the room. Okay, let's see what people said. So the input is a vector of size. 3 people said 1. 5 people said 26. So is it 1 or is it 26? So a vector of size 1 is a number. That would be like inputting a number. And a vector of size 26 would be like 26 different numbers. I guess let's see what you wrote for the blank encoding, because that might give us a hint. The blank encoding, all right, this is great. So some people said 1 hot. So 1 hot, 1 hot. I don't know. It's a good answer. Label encoding. So one possibility. I think we've basically come up with 2 possibilities. There is one possibility. This is really fantastic. There's one option. One option is you set A to be 1, B to be 2, C to be 3, D to be 4, Z to be 26. And then you just input the number 1 to 26. So you say like it goes in as the number A, whatever letter it is, Q I guess is some number. Should I figure out what number Q is? What letter of the alphabet is Q? I'm going to do a Google search. Q is which letter of the alphabet? Q is the 17th letter of the alphabet according to Google. So maybe right, maybe not. Okay, so Q goes in as 17, and then you take the number 17 and you do stuff to it. Like you multiply it, right? Those are the things we were talking about. You multiply it, you do ReLUs, you do all sorts of stuff to it. That's the neural network part. And then you get the outputs. That's one possibility. Okay. And then the other option is to use the 1 hot encoding. So a few people talked about 1 hot encoding. And that would be something like A becomes the vector 1, 0, 0, 0, 0, 0, 0. And B becomes the vector 0, 1, 0, 0, 0, 0, 0. And C becomes the vector 0, 0, 1, 0, 0, 0, 0, 0. Right? And in that situation, you have a vector of size 26. So Q becomes the vector which has 16 zeros, 0, 0, 0, 0, 0, 16 zeros. Then it has a 1 in the 17th spot, and then it has all zeros after that. And that goes into the neural network, and then we do like matrix multiplication and all sorts of all the like vectory type stuff we were doing before. So those are the 2 options. And actually, we've done this exact thing before way back in the class when we did linear regression, right? There were some features in the housing data set, like housing quality or something, right? And it was like, should you put in the housing quality as a number from 1 to 10, or should you say like red, green, blue, and have like a thing? So this issue of should you do this first option, or should you do 1 hot encoding? I think this one is called label encoding. Maybe I'm wrong. Someone correct me. Is that one label encoding? Label. Okay, people are nodding. So, and sometimes label encoding makes sense. Sometimes 1 hot encoding makes sense. The question is, in the neural network, which one do you think makes more sense? So great, we got 2 good options that are pretty closely split for the input. Let's look at the output. And of course, we're going to do a revote. But let's look at the output. So the output, people all said, should be a vector of size 26. Or most people, 6 out of 8 people said 26, which is a good majority. And we interpret the outputs as probabilities by using, some people said softmax. Softmax was common. And logistic regression is also softmax. So I think there's a good consensus here on what to do on the output. So the input we don't know yet, but on the output will, so the neural network will do some stuff to whatever the input is, and at the output we'll get a vector of size 26. So maybe we'll get like 7.5, -3, 100, -0.5, and we'll have 26 numbers. And we have these 26 real numbers, so this is a vector in R to the 26. And to convert it into probabilities, you take these numbers, you do e to the power of each number, and you divide by the sum. And that's the softmax function that we looked at last time. So you do softmax, and so the probability of, say, the first letter, it will be e to the 7.5 divided by the sum of e to the, let's call it OI. O stands for output. So you take this value of 7.5, you take it to the you do e to that power, and the probability is proportional to that. And you make it so that it all adds up to 1 because it's a probability. And you do this for every single thing. And so you can convert this probability into, sorry, you can convert this vector of all numbers into a probability vector of positive numbers that are between 0 and 1 and add up to 1. That was what we did last time. That's called soft max with an X. Okay, there we go. Soft max. And we talked a little bit about that last time. Logistic regression with 2 classes is exactly the softmax function. This idea is exactly how you make probabilities from vectors. Okay, so that part I think most people understood. The first part, we're not sure, should we do the label encoding or should we do the one-hot encoding? And I will let you revote, so let's do it again. Repeat. Okay. And what do I gotta press? Start. Start. And present. Okay. Oh, that's not that's the wrong one. Okay, I want this one. Okay. Okay. So there you go. Same question again. You're essentially voting between 2 choices now. You're gonna have to put in all your answers again, but that's good too. So I'll give you 1 more minute to decide which do you think makes more sense for our neural network. Okay, there's like 20 seconds left. Put in your guess, either label encoding or one-hot encoding, either 26 or 1 for the size of the input, and what? The output we already know. So the output should be 26 and softmax. Okay, good. We're up to 10 answers here. Let's see what people said. Okay, now we're 8-3. So 3 people still in 1, but now we're 8-3 of size 26, and 7 people said one hot, 3 people said, 8 people said one hot, and 3 people said label. The correct answer that we're going to do is use 26 and use one hot. And again, the reason is exactly the same reason as in linear regression, which is if you do label encoding, you have already made a choice for the computer. And you have said that anything you do for a B is going to be twice as much as for an A, right? So like the probabilities at the end of the machine will come out to something. Are they twice as much for an A as they are for a B? Like, no, that's silly. Like a B has nothing to do with an A. Like a B is its own separate universe from an A. A and B are totally different letters. We should not tell it that B is twice an A. It is true, and maybe this is the confusion of the people who voted for label encoding. We really are not doing label encoding. We really do want to do one-hot encoding. But at some point in the code, you will see A is 1, B is 2, and C is 3, and so on. And that will become this stuff. So we'll say, like, put a 1 in the first column. And how do you put a 1 in the first column? You say 1. You say one-hot encode the number 1. So if you were thinking that, maybe you wanted to do label encoding first, and then the very first step would be to do one-hot encoding. But you certainly want to actually, the actual thing that goes into the neural network is the one-hot encoding. So great that most people figured that out. Any questions or comments about that? Okay. And the output we already said is going to be softmax. And so this is the fun thing about neural networks is you kind of like know what the input and the output are. You kind of have a sense of what are the possible things you can do, and you get to like build a bridge between them. So we really have this situation where we're going to input the letter Q, right? So the letter Q is going to become this vector 0, 0, 0, dot, 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 with a 1 in the 17th position, and then all zeros after that. And then we want it to output high probability on U. So this is what we want, is we want something like U. What letter is U in the alphabet? Things you should look up before class, but you don't. Okay, U is which letter of the alphabet? 21, apparently. Okay, 21. So U, the 21st letter. Okay, I guess we don't want it to be, it's probably not going to be 1. It's going to be like 0.95 if we're very lucky. We'll have like 0.01 everywhere else. I don't know. The 21st, and then the others will be small numbers, 0.01, 0.1 all the way up to. Right? And that's going to come from a softmax with a vector that has a large value, maybe like +7 in the 21st component, and like negative numbers, -2, -3, I don't know, -5 in the previous one. So this is like the pre-softmax. The pre-softmax has a name. That's the logits, or logits, depending on who you ask, right? So we're going to input this one-hot vector, which is the Q. It's going to go through our machine, which is this blob in the middle that we're going to fill in, the neural network machine. And then the neural network machine will output the logits, which is some vector of numbers, and then we'll do a softmax at the end and compute what it is. And what I have described for you, every neural network is like this, right? Because I've just left it as a blob. So even the most sophisticated, like ChatGPT, really does work exactly like this. Okay, maybe that's a lie because ChatGPT has more than one letter at a time, right? So that's the only thing that's different. We're inputting one letter here. ChatGPT would input the last 10 letters, and then it would do that. But the kind of philosophy is exactly the same. You input the things as one hots. They go through the neural network. You get them out as logits, and then you can get the probabilities. Okay. And so now the question is, how are we going to fill in this thing? And we're going to start with the simplest possible thing, which is the same kind of thing we did last class. Because we did it for MNIST, and we had, in MNIST, we had this situation, where we had no nonlinearities, and we just did 2 matrix multiplications. This is the world's simplest neural network, is actually just matrix multiplication. In this case, because of the way we trained it, we said we want to reconstruct exactly the output. We want whatever you put in to be the same as whatever you put out. That was for MNIST. We were doing this autoencoder. So you input the image, you condense it down to some number of layers, and then it comes back to reality, and you say, I want the condensed version, the recovered version, to be the same as the input. That was an autoencoder, and that is exactly the same as PCA. We're going to do this exact same architecture, but of course the question we're asking is going to be different. Because we don't want the same letter to come out, we want the next letter to come out. So let's go to my blob. So we're going to start with, we're going to do the simplest possible thing, which is we're just going to do 2 matrix multiplications, no nonlinearity, nothing like that. So 2 matrix multiplications. So I'm going to have some lower dimension over here. And in PCA and stuff, we interpreted that dimension as the dimension we're condensing down to. So maybe we'll have like 5 dimensions. So we're going down from 26 dimensions down to 5 dimensions. We'll have a vector of size 5. I guess I'll draw a vector as a vector. 5-dimensional. This is the sort of the hidden layer, or the low dimensional representation, right? And to get from the input to there, we're going to do 1 matrix multiplication, and to get from the hidden to the logits, we're going to do another matrix multiplication. So this is going to be some layer W0, and this is going to be some layer W1. And that's what we called them before. And you can really think of this as like, these things are connected to every single thing, right? So W0 is a 26 by 5 matrix, and W1 is going to be a 5 by 26 matrix. And if you do that, that's like the world's simplest linear sort of neural network. There's no nonlinearity. And you can interpret these as vectors. So just like we did in PCA, you can say, okay, it's a neural network that's really simple, or you can say it's doing vector representation. And how is it doing vector representation? Well, W0 is 26 by 5. So 26 rows, 5 columns. You can interpret those 5 columns as the vectors, right? Or okay, more accurately, so you have 26 by 5. So 26 rows. So here's W0. 26 rows by 5. By 5. And you can interpret each row of this as a vector of size 5 that is the representation of that letter. So for example, the vector in the first row, this will be a 5-dimensional representation for the letter A. The letter A. And that makes sense because when you do a one-hot multiplication, when you multiply by 1 and all zeros, then you're pulling out the first row of the matrix, right? You're doing a matrix. I might have, okay, depending on how you multiply here, I might have the sizes backwards. But I want it so that it makes sense, right? So 26 by 5, I guess if you're going to multiply a vector of size 26, it should be the other way. It should be 5 by 26 maybe. Okay, let's make it 5 by 26 so everything adds up. 5 by 26. Let's do it like that, 26 by 5. And then that way, I can really write the formula. I can really write the formula down here. If it will let me. Okay, I can write the formula as the output, or the logits. Let's say the logits. It's going to be W1 times W0 of the input. And the input is a one-hot vector, so it's 26 by 1. The W0 is 5 by 26, and the W1 is 26 by 5, and it all works as matrix multiplication. So what I wrote down is wrong over here. It should be the other way. So let's try it the other way. So here's W0, and it's 26 columns, each of size 5, 5 by 26, and you get the first column. So this first column is the representation, the 5-dimensional representation for the letter A, and that makes sense because when you multiply by the vector 1, 0, 0, 0, 0, then you pull out the first column. When you multiply by the vector 0, 1, 0, 0, then you pull out the second column, and so on. So W0 of 1 hot I is column I. Column I. So that is the simplest possible thing you can do. You just have two matrices. You can make it even simpler by saying we have two matrices. The W0 is sort of the low-dimensional representation of the inputs, and the W1 is the low-dimensional representation of the outputs. But we're doing letters, and the inputs and the outputs are both letters. So you can make things even simpler and say, look, I'm looking for one vector representation. So the even simpler thing you can do, even simpler, let W0 equal W1, and it has to be transposed because of the way it's working over here to make everything work out. And that makes sense because you're saying going from the input to the low-dimensional representation, those are vector representations, and it's the same thing the other way. So if you had a vector that was all zeros and a 1, then that would be the same vector representation. Okay. And this is the first thing I'm going to do. So we're going to do this example in detail. I have a really nice short Python notebook. Well, we're going to do this exact example and see what it outputs. But are there any questions or comments about the theory here, or the setup? Okay, let's see it in action. So this is called, I made this thing just for you guys, called letter2Vec. Letter2Vec. And it is built off of these Make More series of videos that I talked about before, and I linked in the things to watch. So you have a vector embedding for each letter, VA, and if you stacked all the vectors together, you would get the thing I called the matrix W0. And if you write down what this thing is doing, if you write down, so W0 of 1 hot of I is column I, let's call that VI, then W1 times W0 times 1 hot of I, if you look at the jth component, this is the logit number j. So let's pretend that you want to know what is the entry over here, right? So I say when you input a q, when you input something which is a 1 in the 17th component, and you output something that is the logit in the 21st component, that is looking at the entry that I'm talking about over here when I equals 17 and j equals 21. So logit number j for input number 17. It turns out that this is equal to just the inner product of vi with vj. Right? So if you want to know how much is the logit j, you just do the inner product of the vector representation of the letter for q with the vector representation for the letter for u. So how likely QU is proportional to, you got VQ and you got VU, and you have these vectors and you just do their inner product, and that tells you what it is. So it's doing matrix multiplication. Matrix multiplication and inner products are like the same thing if you have the dimensions set correctly. And that is what I have written here. So what I did before, I wrote it in terms of matrices, but I've described it in this document in terms of vectors. So I'm saying we have these vectors, VA and VB, and the probability that the next letter is the letter A, given the previous letter is the letter B, is proportional to the exponential of this. Why is it the exponential? Because that's the softmax, right? So the logit is just the inner product, and the probability to go from the logit to the probabilities, it is the exponential. Okay. Okay, and we're going to do it like we always do. We're going to start with a random collection of vectors, and then improve with gradient descent, and see how well we do. Okay. The very first step, which I briefly described last class, but what we're going to do in detail now, is how do you make the actual data set? And the data set is going to be a bunch of pairs of letters. I'm going to go through my whole data set, get the pairs of letters, and I'm just going to write down, okay, there was a Q, and then after that there was a U. So one thing in my data set is QU. And then another thing in my data set will be BA, and so on, right? I'll have every possible pair. So we'll see how that works. Okay, so let's go down and check this out. Okay. So, and I set up the beginning exactly the same as from that video series, and I'm using the data set of baby names. So this is the names.txt. There's a bunch of baby names, and here are the first 5 rows of the name, or 8 rows of names.txt: Emma, Olivia, Ava, Isabella, Sophia, and so on. These are a bunch of baby names. I think they're like the most popular baby names from some year. And there's 32,000 names, and we're going to use these as our data set. So the first thing we do is we chunk these into 2-letter pairs. So I do EN is a pair, MM is a pair, MA is a pair, and so on. And that's creating the data set. There's one extra thing that I add, which is I add to every single word, I add in a end of word token. So I'm going to put a period after each one. I'm going to do Emma period, Olivia period, Ava period. And period will be my special 27th character. That means end of the word, like stop writing. Okay? And so that's what is going on here. And this part is taken exactly from Andrei Karpathy's stuff. So if you want to see the details, you can see that. But I have an alphabet size. It's not 26, it's size 27, because I have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, all the way up to Z, but then also including dot. And dot means end of the word. Okay. Okay, and then I make my data set. So here's the data set, and it's just you loop through the whole thing and you build it. Should I output some of them? Well, okay, you know what we can do? Let's run everything. And okay, let me run before. Yeah. Okay, and let me run this one. Okay, and then I have a training set and a test set, and I'll show you what they look like. So they are, right now, they are vectors. So if I look at X training, what does that look like? So it's 0, 25, and so on. And if I look at Y training, it's 25. So that says the first example, the first letter was the 0th letter. And then the answer, the letter that came after that was the 25th letter. So it was an A followed by, I don't know what the 25th letter is. I guess Y? A-Y. So there you go. That's the first example. I guess they were all shuffled up when I did training and test. Can I? Yeah, so they were shuffled. If you didn't shuffle them, then it would really be E and M and so on. But okay, hopefully this part is okay. So right now, they're label encoded, and we have the input letter and the output letter as different things. We're going to one-hot encode them in a second. And we have a train set, a test set, and a def set. Is there any questions about what's going on so far? Okay, let's keep going and see how things are built. So now we're going to set up the vectors, and I make V. This is the big kahuna here. These are our vector embeddings. So I made the embedding dimension 6 in this example, and I am embedding them by starting with completely random vectors. So what is the vector embedding for the letter A? It is a completely random vector of size 6. What is the vector embedding for size B? It's a completely random vector of size 6. Okay? And it's arranged, you see, in a 27 by 6 matrix. Really, this is the matrix W0, but I'm thinking of it as V of A is the vector for the letter A. So V0, V1, V2. And so I'm thinking of them as vectors to make it a little more easy to do. This stuff is done in the torch library. So last class we used the JAX library, and in JAX you just use the grad function and everything works. In torch, the gradients are a little bit different, and you have to tell it I'm going to do the derivative with respect to these vectors v. So please, I made a list of parameters, which right now is just v. And I said, please make sure you keep track of the gradient with respect to every single entry of v. And that's what we did. Okay. And here's the training. Here's the training. What is the training? You're going to see it's a very simple thing. It's all over here. This is all the magic. It's one matrix multiplication. So I do v of the examples you give me. I'm going to look at some set of examples. The set of examples you look at is called the mini batch. And I do x train of the mini batch. And x train of the mini batch means take out those examples. And the mini batch is chosen randomly. It's a random integer between 0 and the number of examples we have. So we have like 10,000 examples. I say pick example number 700, example number 720, example number 8,000. Pick a bunch of them at random. Do 256 of them at once. And just get all the embeddings. So v of that thing. So v of the entries. By writing it this way, I've avoided a matrix multiplication. You could have also written it as v times the one-hot encoding of the thing. But of course, when you're doing a simple vector, that's the same thing. So you can either do v of the thing, or you can do the one-hot encoding. And then I do a matrix multiplication. This is exactly W0 times W1. Do you remember W1 was W0 transpose? That's where it is appearing right there. So this is doing the predicted probability logits by exactly feeding in through our network. Okay, so it's exactly this picture over here. First, we take some examples. We take a bunch of examples. We feed them through here to the low dimensional rep. Then we feed them up to get the logits. And both are matrix multiplications. So we've implemented this matrix multiplication. W0 times the input, that's what we call v of the input, and then multiply by v transpose, because W1 is V1 transpose. Okay, that's what it is. It commented out over here is the stuff that was in the original version. So this is like a simplified version from the video. We'll talk about this one in a minute. And then to get the loss function, I'm taking the logits and I'm calling the cross entropy loss function with the true answer. So the true answer is y train. That's what we wanted. The real answer was u. And what is your loss function? Just like before, we do softmax and we do the cross entropy, and it's all included in this f dot cross entropy function. So I've computed the loss function, and then we do the gradient. So this is computing the gradient. In the other package we used, JAX, you call the gradient as a function, and this one, the gradient is attached to the parameters. So first I set the gradient to 0 on everybody, and this funny function, loss dot backwards, will set the gradient of every single parameter to whatever the derivative is. And then we do a step. This is plus equal the learning rate times the gradient. So change the value of the parameter by adding on a little bit of the learning rate times the value of the gradient. And it's really important you put a minus sign there, because we are doing gradient descent. We want the loss to go down. If you put a plus sign there, then it would get worse and worse and worse. Okay, and then the rest of it is bookkeeping. So it's bookkeeping the loss. Okay, how long does this take to run? I think it's pretty quick. Let me try running everything. I think I only skipped running some things. Yeah, it says v is not defined, so it must have not run the one where I did this. Okay, ran that, and now we're training. Okay, so there you go, and it's pretty quick. Questions or comments while the computer is training? So we started with random vectors v. We computed how well are these vectors v are at predicting the next u, and then we're updating a little bit. We're seeing to update a little bit, and we see how it does. Okay. And if we keep going down, it plots. This is the loss as a function of time. And it's averaged. So we're doing these mini batches of size 256. So if you just plotted the actual loss you got, it would be up and down and up and down and up and down, because you're getting random examples. Maybe you get some examples that are hard, some that are easy. But if you do the average over the last 1,000 inputs, you get this nice smooth curve, where our loss started at like 3.1 and it ended at like 2.8. 2.8. By the way, you can interpret this loss quite easily, because in the cross entropy loss, remember we had the formula for cross entropy loss. Cross entropy loss the formula is minus the log of the predicted probability, true. So if the true answer is U, the loss you get is minus the log of whatever you said the probability of U happening was. So if this is 2.8, we can reverse engineer this to see that what we're getting is the true probability, the probability we assigned to the true thing is e to the negative 2.8, right? And so what is e to the negative 2.8 these days? Let's find out. Look, here is the Google search where I looked up what letter of the alphabet is U is, and now I can do e to the power negative 2.8. And it's 6, 0.06. So what this is saying is when our loss function is, when we're getting a loss of 2.8, that means that on average, our method is saying U has a 6% chance of being the right answer when U is the actual right answer. And it does that on average. So that's not great, right? That's not great. We would like it to say like 95% when U is the right answer. So 2.8 is not too great. And it gets down all the way. That's about as low. We started much higher, and we got down to 2.8. It's all on an exponential scale, right? Because it's e to the power of this. So small differences can add up quickly. Okay. And I did it. I checked on the training set and the test set, and it's all about 2.8. So 2.79, 2.79, 2.8. Here's the fun thing you can do, is you can visualize the result as a big graph. So here it is. These are the vectors in R5. Every single letter has a vector in the embedding dimension. I think I made it 6. So every single letter is a 6-dimensional vector. I have a 2-dimensional board. So how did I plot 6-dimensional vectors on a 2-dimensional board? One thing you could do is you could look at the first 2 components or something, but I did something even more fun, is I did the PCA. So I did the PCA of those 6-dimensional things, and I took the top 2 and I plotted those. So it's PCA1 versus PCA2, and these are what the letters look like, right? So we found a vector for every single letter, and if you want to know how likely two letters are to occur next to each other, it's the inner product of the 2 vectors. So if the 2 vectors are very close together, that means that they're likely to come together, and if they're not, then they're not. And look, something cool is happening here. You see U and Q? You see how they're in the same direction? Q is also a weirdo letter, right? Q, in terms of who comes next, Q is the weirdest letter, right? Because Q has this like rule, like it's always U. And look, Q and U are in the same direction, that's great. The vowels are all over here, so apparently vowels and like the letter D is like somewhat similar to a vowel, I guess. And here are some other letters that are very different than vowels, like C, H, J are very different than vowels. In a situation where you had a vowel, could you replace that vowel with the letter J? No, they're very orthogonal. Like, vowels go that way, J is straight down. And you can see, the other thing you can do is you can see how well it's doing. You can compute this full matrix over here of all the different probabilities. So this is all the different pairs of letters you can have, including the first column is the special dot character, which means end of a word. And you can see how well it's doing. Okay. And hopefully QU, see, QU is quite a bit, it's a good probability. It's 9%. So it says if you have a Q, the 5% chance it's a dot after, all the way up to a 9% chance that there's a U after. And it actually thinks that there is an 11% chance that an R comes after a Q. That's kind of weird. That's not great. And kind of overall, this whole thing, you can see it really likes some letters. Like some letters it just really likes for every single value. And other letters it just doesn't like very much at all. So it really likes the letter E. It thinks there's a lot of E's. And it really likes the letter A. That's this other column over here. And just like QA is very likely. Where's my boy Q? A little further down. So like QA is 6.6 is almost as likely as QU just because A is so likely, right? Like A has to just be high. QI is 7.7 is almost as much as QU. So, you know, it's kind of not great. Kind of not great. But we got something. And here, this is the really fun part. This is the funnest part of the whole project, is you can use this to generate random baby names according to our thing. How do you generate random baby names? Well, you start with nothing. You pick the first letter, and then once you know the first letter, there's probabilities to pick the second letter, right? What's the probability that the second letter is whatever? You pick out a second letter at random, and here are the names that the machine came up with. Okay, these are not great names. If you saw these, you would not think these are like names. Especially this one. This one just goes on forever and ever, right? And that's because it doesn't know like how long the word is. It only knows what is the previous letter. So if you just know what the previous letter is, you just like go on for a long time. I guess, yeah, Ron, that's a name. That's good. We got one. The rest are quite bad. Doesn't look very namey. Okay, we're gonna improve it in 1 second. But this is the simplest possible one. And everything we do is just a fancy version of what we've done so far. Just making it more and more fancy. All the way up to, I really think that all the way up to ChatGPT. Like if you understand this, you've understood most of the like how it works, right? The rest of it is details on like how exactly do you put it in the neural network and how exactly do you train it, but this is most of the stuff. Any questions or comments? Okay, so here is a question or comment for you guys, and this is one thing that I don't like about our current model. So right now, we're doing it, like I said on the previous slide over here. We have this inner product, the VQ, VU. So QU depends on the inner product VQ, VU. But you know what else is the same as VQ, VU? There's a fun fact about algebra, that VQ, VU is the same as VU, VQ. So inner products have the property that if you switch the order of the vectors, it's the same value. And in our setup, VQ, VU and VU, VQ are two different letter combinations, like UQ. Okay, so QU is this one, and UQ is that one, but mathematically these are the same. And therefore, our network kind of thinks that a Q followed by a U is doing the same kind of thing as a U followed by a Q. It's not exactly the same because the proportional to is different, right? The set of vectors you add over is different, but they are related. And so here's the question for you guys. Take the very simple thing we just did in the code and got these things. How could you improve it? And when I say how could you improve it, so a QU will also make a UQ, right? Because of this inner product thing. How could you modify things so that QU and UQ are not related, right? I want kind of to have QU and UQ to be their own individual things so I could change the probabilities separately. And if you take what we did and how we got here, there's one simple thing you can do to make them different. Okay, so I'll give you guys a minute to think, pause and ponder on what it could be. Feel free to talk to your neighbors. What could you do? Okay, and while you're thinking, I'm going to get water. Okay. 10 seconds left. We have two ideas. It's okay if you don't have an idea for this. We're looking for just different ideas. All right, let's take a look. Very curious what people said. Typical bug. Few responses, okay. Vector product are used 2 letters at a time. Okay, this is a great thing you could do. So you could somehow do 2 letters at a time. And in fact, the thing after the thing I'm going to do now, we're going to look at how you would do even more letters at a time. And that is part of the secret of how ChatGPT works, is it doesn't just do 1 letter at a time, right? It looks at a very long window, and it can say, oh, you should probably end the word here because it's quite a long name already. This is a name that's already gone on for 10 characters, and there are not many 11-character names. So if you have a name, you've got 10 characters already, you should probably stop. So that is one way you could definitely improve it is by using multiple letters. And I'll talk about that in a second. But I want to do something that has the exact same data set. So just with 2 letters, how could you improve it? 2 people wrote vector product. So if by vector product you mean dot product, maybe you mean something else. Someone want to say what they mean? I'm not sure what vector product means. Yeah.
Like as we are doing scalar, like first we are doing dot product.
Yeah.
So in that you have said that Q and UQ are the same thing that we are multiplying.
Right.
Rather than if you do Q cross U, then.
Okay. So do a type of like a matrix product where the order is different. Right. Okay. Yeah, that's a great idea. How do we put that in? Yes. No. This is a really wonderful idea. I'm not sure how to implement it. Yeah. So the thing is, it needs to be a number at the end of the day because it is the logit. Yeah. So on the face of it, I don't see directly how to do it because at the end of the day, you want to get just one number. I guess what you could do is you could add more layers. If you add like 3 layers and you have a bunch of like weird stuff going on in the middle, then the output, instead of being like VQ, VU, it'll be like VQ times a bunch of weird stuff times VU. And then if you flip it around, it'll be VU times a bunch of weird stuff times VQ. And then you have this matrix product in the middle, and then they won't be the same. So this is, I think, one way you could make that work is just by adding more layers, which is something you could definitely do. So that's a great idea as well. But there is one much simpler thing, and the way I started the class was actually, we got to this VV situation by doing this thing right here. We said, let's make W0 and W1 the same matrix, right? We had vectors going in, we had the input, and we had the output, and let's use the same matrix for both. And that's because we said we have these vector embeddings. The vector embedding for the input and the vector embedding for the output wouldn't it be nice if those were both exactly the same? And when those are the same, you have this really nice interpretation of what the vector embedding means. It's both telling you the input and the output. So if you want to know how alike Q and U are, then you just look at the graph that we generated. This one, right? You just look at this graph and you say U and Q, they're in the same direction, so that tells you how likely QU is and how likely UQ is. But there's no reason these have to be the same. You could actually make these 2 different things, and that is the next level up that I have. So this is the same thing with 2 vector representations. So instead of having a vector V for every single letter, I have a vector V for every single letter and a vector W for every single letter. And how likely QU is will be VQ inner product with WQ. And that is really exactly thinking of the input and the output as different. So we have an input vector compression and an output vector compression, and they are different. So we have V going in, and we have W coming out. And they are 2 different things. So V is like the input, and W is like the output. And that way, VU, WQ has absolutely nothing to do with VU, WQ, right? They're just like completely different vectors. You've switched on where you attach the labels. And that's just making the W0 and the W1 totally independent. Of course, this doubles the number of parameters in our model. But the setup is exactly the same. So let's see how this works. So here, instead of having just V, I have V and W. The parameters are now V and W. I do the same gradient thing before. And I do the same training as before. So exactly the same thing. Everything is the same. The only difference is in this line. All the code is identical, except for instead of doing .v.transpose, I do w.transpose. So you embed, this is the embedding with V, and then you go from embedding to logits with W. Okay, and then I trained it. Fortunately, I trained it while we were doing something else, and you get a little better of a score. So before it was 2.8, now it's like 2.5. That's great. So big improvement. All the way from 2.8 down to 2.5. We can go to Google and say, okay, well, what would that be? Right? E to the power minus 2.5 is 8%. So we're getting the correct answer. Instead of saying it has a 6% chance of being right, the correct answer now has an 8% chance of being right. That's an improvement. That's like a 25% improvement in relative terms. Okay, let's see what it looks like. And then now the nice thing is we have 2 graphs. So you have 2 graphs. You have one graph on how the vectors look as an input, and you have a different graph, which is how they look as an output. Okay, well, let me do this. Okay, so here's the input graph. I guess I need to zoom out even more to fit it. there's the input graph. Okay, you guys probably can't see the letters, but look, in yellow I have all the vowels. So A, O, E, U, oh, I and Y are down here. But all the vowels are kind of clustered together. Q is again a weirdo, right? Q as an input is a really weird input to have. If you have a Q, something special happens. But on the bottom are the outputs, and they're very different. So the outputs can be as different as you want. Okay. So here are the outputs, and let me see, where is U on here? U is just like a regular looking guy now. Because U can come after all sorts of letters. And is Q a weirdo over here? Anyway, Q is over here, so it's not that weird anymore. Because as a second letter, you can have all sorts of things can come. Q can come as the second letter in all sorts of things. Okay, and then the real test is you can look at how does it do for this matrix over here. And look at this. QU is now a 70% chance. Right? So after a Q, a U happens with 70% chance. That's pretty good. And actually 10% chance is a dot, which is, would say like a word that ends in Q. Some people like baby names that end in a Q to be very different. But this is a lot better than it was before. So if you have different vector representations for the input and the output, you can get a much better score, and it can look like this. Okay, and this is the fun part, is we can now look at some names that were generated. And I claim these are better than they were before. You guys, this, of course, is completely subjective. But I like this one. Allelevelin. That's nice, great. See, again, sometimes it just goes on for forever and ever, and it gets stuck in a loop. But Koj, what a great name. These are some interesting name names. Okay, so again, not great, but better. Not great, but better. Okay, so that is one way to improve it. Any questions or comments about that? All right. The reason I wanted to show you guys this example is because we did vote and people decided they liked the movie rating data set. So that's one of the possibilities for the movie rating data set. For your final project is to do this movie rating prediction thing. And for movie ratings, everything I just did, you can do for movie ratings. So instead of thinking of what is the first letter, what is the input letter, and what is the output letter, you can think of who is the user and what movie are we rating. So everything we did so far will work for movie ratings. We had an input letter embedding, input letter. So we said the letter Q becomes the vector VQ, and then we had an output letter embedding. So we had the letter U becomes the vector WU, and then how likely QU is in data set. That was the inner product VQ with WU, right? Okay. This was the logit, you had to do the softmax and all that. But you can do the exact same thing for any kind of like system where you have lots of pairs of things, like the movie system. So you could say you have the movie embedding. Okay, so I don't know, what's a good movie? What's going to be my example movie? Terminator. I don't know why. Terminator. So that's a movie. You have like 9,000 movies in the data set. Every single movie is going to get its own vector. You're going to embed that into the vector V Terminator. Okay, and this vector somehow represents who likes this movie, right? Like if it has a large first component, that somehow goes with the users having a large first component. So this is the movie embedding, and then you can have the user embedding. And so there could be like some guy, Bob, I don't know, Bob, and Bob becomes a vector W Bob. And your prediction of how much Bob likes the movie The Terminator will depend on the inner product V Terminator. So how much they like it, how much they rate it. V Terminator W Bob. Okay, and once again, there's some pre-processing you have to do, because an inner product can be a negative number. So just like this was a probability, and I said you make it the inner product, you actually have to do a little bit of work, like softmax or something. Here you want to, instead of getting a probability, you want to get a number of stars between 1 and 5. And probabilities, they have this property that they add up to 1. there's no reason star ratings have to add up to 1, right? Like I can rate every movie I see can be a 5-star movie for me, and I can do a bunch of 5-star ratings. There's no reason they have to add up to 1. So it's not exactly the same, but the core idea is exactly the same. You have a vector embedding of movies, you have a vector embedding of users, and then you use this inner product to predict whatever it is you're predicting. And when you go in the training set, you'll have a bunch of movies that Bob liked. You'll have a bunch of users that like the Terminator movie. And if you use these inner products, it will sort of like find them automatically. In the same way it did it for the letters, right? Like it automatically found in our training set that Q followed by U, where's QU? Q followed by U was like 70%. Like how did it do that? Well, in our training set, whenever there was a Q, a U happened after it. And so by gradient descent, it learned that the vector embedding for Q and the vector embedding for U should go together a lot, right? That should be a really big inner product. And just like that, it'll work for your movies too. So if you have people who like the Terminator movie, if Bob is like those people, then that should be a high number, right? It should move it up. And that's like roughly how it works. This is also sometimes goes by the name low rank approximation. This is sometimes called low rank approximation or low rank filling. And the reason it's low rank is because the rank of the matrix you get is always the size of your vector embedding. So if you do movie embedding, if that's a matrix, times the user embedding, that's a matrix, that will be the rank of this is the rank as the size of the vector embedding. And so if you do like a 6-dimensional vector embedding, you have this matrix which is like thousands by thousands potentially of all the users and movie pairs, but you're approximating it with a low rank matrix, which is like dimension 6 or something. I don't know what dimension you would need. You would have to play with it. But that's one possibility of what you could do for your final project if you want to. Any questions or comments? Okay. The other really good idea that was in your, that somebody said was, should we input more than one letter at a time? And that is a great idea. And in fact, the lowest possible loss you can get in what we did, so I showed you the loss we got with a 6-dimensional V and a 6-dimensional W was 2.49. It turns out the lowest possible you can get, even if you are absolutely perfect, is 2.47. You cannot beat 2.47. Why can you not beat 2.47? 2.47 is what you get if you get this matrix perfectly right. So if you just memorize this entire matrix in the training set, like if you know the actual probability of a U following a Q in the data set, no U's, no V's, no W's, you just memorize this entire matrix, then you are still only able to predict the next letter with quite low confidence. And the reason is just 2 letters is not enough, right? If you just know 1 letter, the next letter depends on all sorts of other things. So even if you are predicting as well as you possibly can, you are not going to get it. So what we did is actually, we've approximated the true matrix using a rank 6 matrix. In principle, it could be rank up to 27. But this low ranks approximation is good up to the 3rd decimal place. So we got 2.49. The best you can possibly do is 2.47. If you want to make it better, you should look at multiple letters at once. And that is exactly what is done in the video. So if you watch this video, he has this picture over here of how it's working, and which comes from this paper from 2003. So this is a paper which is now 20 years old. And how do they do it? This picture should remind you of the kinds of things we've been doing, and you can very easily explain what it is. So instead of having an input, which is of size 26, they have 3 inputs of size 26, and all 3 of them use the same matrix C. They say share parameter across words. That is a vector embedding. So what they're doing in our notation, let's make a new page. They have the same vectors. So if it says C-A-T, I don't know, then they take the letter C, they turn that into a vector. So I guess really what they do is they one-hot 0, 0, 1, 0, 0, 0. Then they multiply by the matrix W, the embedding matrix, W, what we call W0, and they do the same thing for A. So A gets the same W0, and they make a vector embedding. I was doing that of size 6. So 6, 6, and T will be some other letter. 0, 0, 0, all the way up to 1, 0, 0, 0. Same vector embedding So same vector embedding for all. Okay, and then you stack those together. They stack them together in this latent space to make a vector of size 18. And that goes into what they've described. So that's the input. This is like the input embedding. And then the output embedding is much more complicated, because first they put it through a nonlinearity. So they're doing tanh. We were doing ReLU before, but they're doing a nonlinearity, which already makes it possible to do all sorts of wild, wacky, exciting things with a big, they can then make a very wide hidden layer here, and then they do the softmax and all that. And they do really big, in this one, why is their softmax so big? Because they are doing word embeddings, and there's like 10,000 words in the English language. So they're predicting which word will come next. So that's really big. So they do a low, the vector embeddings are low dimensional, but the softmax has to be very big. And if you want to see the details, I really recommend this movie, or this video, not this video. This video is really, they spell everything out and they go through all the details, and you get, at the end of the day, you get this code, which I copied. It's in our GitHub as well, with some small changes. But the data set is exactly like we did it before, same data set. And you can see exactly how it's trained. And the important thing is when you do the training set here, the x's are no longer just one dimensional, there's 3 dimensions for the x's. So I'm taking the last 3 letters, not just the last letter. Okay. So here are the examples, right? Emma becomes ... E, ... E, then an M. After an E and an M is an M. After E, M, M is A, and so on. So the training set contains longer windows of context. After MMA is dot. Yeah, you end the sentence. Okay, and I will skip running it, but I will just show you. So it takes a little bit longer to run, but the loss you get is much better. You get down to a loss. The training loss is only 1.9. But it is overfitting a bit. The test loss is still like 2.4. So you can fix this a bit by doing all the techniques we talked about to reduce overfitting. So you can improve it, but even as is, you get a really nice vector embedding that looks like this. And again, this is only the input embedding, right? So all the stuff about the output is not here. This is just the vector embedding of the input. But you can see, for example, the vowels are very clearly separated. A, E, I, O, U is on top. And if you do this, the most exciting thing is you get some really nice baby names. So these are looking much better as baby names. So Brent's, that's gonna be really nice. Jen Lee, spelled really weird, right? Caitlin is a real name, Grace is a real name. So it's doing a much better job if you have a context size of many things. Okay, there is another project you could do if you want. It's your choice, there's 3 choices. You could do the movie one. A different one is the one with the recipes. And in the recipes, you input many ingredients, and then you have to say what type it is. And if you input many ingredients, you could do exactly this, right? So you could say, I have, let's see what you could do. I'll draw a picture. You could have an ingredient embedding. So you have ingredient embedding. And what you could do is you could embed your ingredients. So maybe the ingredients are flour, eggs, and oil, right? And each of these become a vector in some low dimensional thing. So this is the vector, the ingredient embedding vector. Maybe there's 6 dimensional, I don't know. You get to pick the dimension. And then you could stack these dimensions together, and then you could have a complicated system, right? Output system. Which could be complicated, it could be simple. It's however you want it to be. The simplest possible thing, I guess, is the output would be a vector of size 18, and you just do the inner product of these 3 stacked things with that vector of size 18, or something like that. But you could do some complicated system here, and then you could output a softmax of which cuisine. So I think there's like a bunch of different ones. Is it American? Is it Italian? Right? And so you could have a type embedding as the output. And then you could compare these things. And so by doing that, flour, eggs, and oil together could be different than flour, eggs, and butter. I don't know. There's some countries use butter, some use oil. Maybe it's more likely to be from Poland if it has butter, and it's more likely to be from Italy if it has oil. So you can combine multiple things like that. Of course, it's up to you. You could also do the system only looking at them one at a time, right? You could just take the ingredients one at a time. That's your choice. So that's another thing you could do. The last possibility for the final project is the score. It's like student score predictions, and that one is really similar to like project 1 and 2. So that one doesn't have any kind of like funny like weirdness to it of like how do you handle things. That one is more straightforward. So the other two are, if you want to try something new and exciting, I recommend you try those first two. They're more fun. And yeah, we have like 10 minutes for questions or comments or anything else about the final projects or anything else we did, trying to get ideas. And of course, you should feel free to look around online and find anything that excites you. You can try. Any questions or comments? Okay, well, I'll stop talking here then, and if you guys want to mill around for another 10 minutes and chat with each other. So the due date for your proposal for the final project is tomorrow. But the proposal really is just making sure you have a group and you have picked a data set and you have some idea of like what you want to try. And so there's a Dropbox for that on CourseLink. So on CourseLink, here are all the 3 data sets. Oh, somebody emailed me and said, do they have to do all 3? You have to do one of the 3. So this is a good thing to know. You pick one and do one. So in movies, the recipe or the student scores. The recipe one, another thing I'll say is that the leaderboard is on Kaggle. So if you want to do the recipe one, you have to make a Kaggle account and you submit to the Kaggle leaderboard. But the other 2, I will make leaderboards for. Especially the movies, please make sure you use the training set and the test set that I give you, because I picked the test set only of movies and users who have rated a lot of things. That way it's not like some user who you don't know anything about, right? It's a user who has rated at least 40 other movies. Okay. All right, all right, I said I'd stop. So let's stop, and I'll be around for a little bit if you want to ask any more questions. But otherwise, see you guys at the proposal tomorrow, and then the final submission deadline is in like 2 weeks. Okay.